Introduction to First Law of Thermodynamics. Have you ever wondered how the refrigerator works? What happens in a car engine? Why the air from the air conditioner is cold? In thermodynamics, you study the relationship between heat, internal energy, temperature and work done. Heat is the energy transferred between two bodies due to a difference in temperature. The first law of thermodynamics is an application of the principle of conservation of energy. In this lesson, you will be able to understand the concept of internal energy for an ideal gas, derive the expressions for the internal energy for n moles of monatomic, diatomic and polyatomic ideal gas, understand the first law of thermodynamics, and study the use of the first law of thermodynamics. The diagram shows a container of helium gas. Click Zoom 1 to observe the gas molecules. What form of energy do the gas molecules possess? Answer: the gas molecules possess kinetic energy. The kinetic energy of the moving gas molecules is part of the internal energy of the gas. Click Zoom 2. What do you observe about the gas molecules? Answer: gas molecules attract and repel among themselves. What type of energy do the gas molecules possess due to the forces between molecules? Answer: potential energy. The internal energy of a system is the total kinetic energy and potential energy of the molecules in the system. Internal energy equals kinetic energy of molecules plus potential energy of molecules. An expression for the internal energy U for n moles of an ideal gas may be derived in terms of the number of degrees of freedom F and the temperature of the gas T. Let us now derive an expression for the internal energy for n mole of an ideal gas. Click on each step of the derivation. The expression for the internal energy U of a mole of ideal gas at room temperature depends on the atomicity of the gas molecules. Click on monatomic gas and observe the gas molecules in a monatomic gas. Key in the number of degrees of freedom F for monatomic gas. To check your answer, click Answer. Click on internal energy U to obtain the expression for the internal energy of 1 mole of monatomic gas. Repeat for diatomic gas and polyatomic gas. Compare the internal energy of a mole of ideal monatomic gas and a mole of real monatomic gas, which are at the same temperature. Answer the questions by clicking from the appropriate select boxes provided on the right-hand side. Observe 2 moles of helium gas and 1 mole of hydrogen gas separated by a partition in an insulated container. Click on T1 and then T2 and note the temperatures of the gases. Click on the partition to remove the partition between the 2 gases. Click on T and observe the temperature of the mixture of gases. How is the new value of T derived? The final temperature of the mixture can be calculated using the principle of conservation of energy. Internal energy of helium gas plus internal energy of hydrogen gas equals internal energy of the mixture of gases, which implies 2 times 3 over 2 times RT1 plus 1 times 5 over 2 times RT2 equals 2 times 3 over 2 times RT plus 1 times 5 over 2 times RT. Now click T1 to change the temperature of the helium gas to 200 Kelvin and then click T2 to change the temperature of the hydrogen gas to 100 Kelvin. Click on partition to mix the gases. Calculate the final temperature of the mixture of gases. Then click T to check your answer. Summary. Internal energy of a system is the total kinetic and potential energy of the molecules in the system. The general expression for the total energy in n mole of an ideal gas is U equals F over 2 times nRT, where F is the number of degrees of freedom, R is the molar gas constant, and T is the temperature of the gas in Kelvin. The first law of thermodynamics is a statement of the principle of conservation of energy applied to a thermal system. One version of the law is heat supplied to the system is equal to the sum of the change in internal energy and the work done by the system. Click the play button to supply heat to a gas in a cylinder fitted with a movable piston. When using the first law of thermodynamics in the form delta Q equals delta U plus W, the following sign convention is used. Click the first column in the table. Work is done by a gas. When using the first law of thermodynamics in the form delta Q equals delta U plus W, the following sign convention is used. Click the first column in the table. Work is done by a gas when its volume increases. Click the play button and observe the work done by the gas when the piston is moved through a small displacement dx. Click the play button and observe the work done by the gas when its volume increases from V1 to V2. Click expansion during expansion and observe the area under the PV graph that represents the work done by the gas. Click compression during compression and observe the area under the PV graph that represents the work done by the gas. The first law of thermodynamics can be used to account for the energy supplied to evaporate a volume of water. The water in the beaker is boiling at 100 degrees Celsius. Click on the button to record the heat supplied to evaporate 1 kilogram of water. What is the latent heat of vaporization of water? Answer: 2.26 times 10 to the power 6 joule per kilogram. What happens to the heat supplied to the water during boiling? Answer: part of the heat supplied is used to do work against the atmospheric pressure when water changes to steam. Click the play button to observe what happens to 1 centimeter cube of water when it turns into steam at 100 degrees Celsius and at a pressure of 1 atmosphere, that is 1.0 times 10 to the power 5 pascals. Click Work Done to calculate the work done by water against atmospheric pressure of 1.0 times 10 to the power of 5 pascals. The volume of 1 kilogram of water is 1.0 times 10 to the power -3 meter cube. When 1 kilogram of water changes into steam at atmospheric pressure of 1.0 times 10 to the power of 5 pascals, its volume increases to 1.6 meter cube. Click the play button to calculate the work done by the system. The first law of thermodynamics may be used to explain the difference in the heat supplied to change 1 kg of water to steam at atmospheric pressure 1.0 times 10 to the power 5 pascals and the work done by the system. Click to obtain the increase in the internal energy when water vaporizes. Hence, most of the latent heat of vaporization supplied is used to increase the internal energy of the system. Internal energy equals total kinetic energy plus potential energy of molecules. Total kinetic energy of the water molecules remains constant during vaporization at constant temperature of 100 degrees Celsius. Hence, the potential energy of the water molecules increases. Click the play button to observe why the potential energy of the water molecules increases. An ideal gas undergoes the processes A to B, B to C, C to D, D to A as shown. Refer to the first law of thermodynamics, delta Q equals delta U plus W. Click on the correct sign for each process.